Okay, lesson 11.3 is going to be about your equilibrium expressions. As we talked about last time, equilibrium, and we kind of mentioned K, but the equilibrium just means that the rate of the forward reaction equals the rate of the reverse reaction. We really saw that with the paper wads where it's not necessarily the concentration of the reactants and products that changes. They do remain constant at equilibrium, but it's more the rate that's going to be changing. So the concentrations of reactants and products are not necessarily going to be equal to each other. Equilibrium can be reached from either the forward or reverse direction, meaning going from left to right or right to left. And as we mentioned before, equilibrium is a dynamic process, meaning that it's continuously changing. It has a continuous forward and reverse reactions occurring at the same time. In that simulation with the paper wads, we saw that we had two graphs of what was occurring. And for some of them, we saw the rate drop down. Maybe the other one, the rate went up. But what eventually was happening, that this flat portion signifies that the reaction is at equilibrium. They don't have to be equal rates. It's just that the forward and reverse reaction are happening at the same time. When we look at this equilibrium constant, or K, it's the value of the reaction quotient at equilibrium. K indicates the ratio of the products to reactants at equilibrium, and the magnitude, or like the size of K, reveals the extent of the reaction. This K really does depend on temperature. As we add in heat, we know that our molecules and particles are starting to move faster. So some of the reactions forward or reversed, as we increase or decrease the temperature, that's going to increase or decrease the reaction rate. The equilibrium expression is a mathematical representation of the law of mass action. It shows the ratio of product concentrations to reactant concentrations, each of them raised to their stoichiometric coefficients. So those coefficients that we see in the front of a balanced reaction. For these K expressions or equilibrium expressions, we do need to start with a balanced equation. So the steps on how to find your equilibrium expression are K. Sometimes you'll see that K with a little EQ, which means at equilibrium, or even Kc, which means the concentration, but they're pretty much the same thing. We're going to start with the balanced chemical equation. Make sure that your coefficients are correct. Then we're going to write the products over reactants. Let's say that we had a reaction, and this is not a real reaction, where we have A and B, and then we have it yielding C and D. The little letters are representing like my coefficients. So when I write this K expression, I'm going to put the concentration of my products, like C, and raise it to the coefficient's power. The same for my concentration of D raised to the power over my reactants. I'm only going to include gases and aqueous compounds. So if anything is a solid or a liquid, we do not include it in this equilibrium expression. So it's a ratio of the products to the reactants, and they're raised to their coefficient. For this first reaction, we see hydrogen and iodine reacting to form hydrogen iodide. I'm first going to write out my expression where I have the concentration of my product raised to whatever power the coefficient is over the concentration of my reactant. I'm not going to raise hydrogen to any power because it doesn't have a coefficient. Same with the iodine. Then, because I have numerical values, I'm going to go ahead and plug those in. The concentration of Hi is this 2.0, and I'm going to square that. And then my concentration of H2 is 0.5 molar, and the concentration of I2 is also 0.5 molar. When I square or cube any of these concentrations, I also have to do the same to that capital M. So I'm going to have 4m squared over 0.5 times 0.5, so 0.25 m squared. Because they're both m squared, they're just going to divide out or cancel out, and I'll divide my 4 by the 0.25, so K equals 16. The first thing that you want to do for this is write your K expression. So we have K equals the concentration of our products. I'm going to raise that to what power? 2, because of the 2 coefficient. Then on the bottom, I'm going to have my reactants. You should definitely be paying attention to the state of matter. We only want to include gases and aqueous, and these all happen to be gases, so we're going to include them all. Then I'm going to plug in the given values. Ammonia has a molarity of 4, and we'll square that. On the bottom, nitrogen has a molarity of just 1, and then hydrogen has a molarity of 2, and we're going to cube that. I do have to also square and cube the m. So I have 16m squared over, this is going to come out to be 8. So we have a total of 8m to what power? 4. When I divide 16 by 8, it's just 2, but my resulting power on the m is a negative 2. What that is going to mean is something that has to do with rate laws and order of the expression. And we're going to talk about rate laws in the next unit when we discuss reaction rates. But for now, just pay attention to the coefficient, like dividing the exponents is why we got a negative exponent. But what is K? K is the equilibrium constant, and it shows the ratio of products to reactants at equilibrium. It tells how far a reaction goes. We can quantify this like we got a numerical value in the last 2 examples. If K is greater than 1, that means that there's more products than reactants. The reaction favors the products, meaning like it favors moving to the right or towards the products. It's going to be actively making products. In comparison, if K is less than 1, there's more reactants than products, which means that it's rapidly making reactants and moving towards the left. And if K is about 1, then equal amounts of both. Le Chatelier's principle, this is just kind of repeating again that when a system at equilibrium is disturbed, it responds to try to minimize that disturbance. Like it shifts away from that stressor. Changes in concentration, pressure, or temperature can shift equilibrium. We also included that volume can change that shift, and that we can use a catalyst to speed up a reaction, but it's not used as part of the reaction. It's just lowering the activation energy needed for that reaction to proceed. The system adjusts to restore equilibrium to get back to like that flat rate that's happening at equal times. We're going to compare Q and K. Our reaction quotient is called Q. It's calculated really similarly to how we just calculated K. The only difference is that the reaction quotient uses current concentrations instead of equilibrium concentrations. Meaning like, if you think about the paper wads, as you were throwing them back and forth, we stopped every 5 seconds. So at any point in time, that would lead to your reaction quotient, which is K. Once you hit equilibrium or those flat lines of the graph, that's when your reaction is at equilibrium. So just slightly different. But we can compare Q and K to predict the direction a reaction will proceed to reach equilibrium. Q is the reaction quotient. Calculated the exact same way as K, but not necessarily at equilibrium. So we're still going to do our products over reactants, and it tells us the current ratio of those products to reactants. So Q is at equilibrium and Q is at any moment. And how we compare them. If Q is less than K, the reaction shifts to the right, meaning it's going to keep making more products to get to equilibrium. If Q is greater than K, it needs to shift back to the left to make more reactants. And if Q is equal to K, the reaction is already at equilibrium. It doesn't need to shift in either direction. So with that example that you see underneath, we're going to compare Q and K. We have a K of 5.0 and a Q of 2.0. So if we were just comparing them to which is larger, I would say that Q is less than K. Because Q is less than K, we can say that the system is not at equilibrium. In order to get to equilibrium, which direction is this going to shift? If Q is less than K, we're going to shift to the right to try to make more products. So it's telling us at any point in time, the quotient is less than at equilibrium. So we need to make more product. Here though, if we're comparing Q and K, Q is 1.5 and K is 0.5. So I can say Q is greater than K. Is this at equilibrium? Which direction does it need to shift to make more product? Sorry, to make more reactant, I should say. So it's going to shift to the left. If Q is greater than K, we're going to shift to the left. We're also going to use ICE tables for calculations to track changes in concentration during a reaction. I usually actually refer to them as RICE tables, where R is going to stand for the reaction, I stands for the initial concentration, C stands for the change in concentration, and E stands for equilibrium concentration.